Okay.
This is the standing waves detected using microwaves. Microwave transmitter. This is a microwave probe, which has got a built-in speaker, so you can't hear microwaves ordinarily. The probe will, whenever it detects microwaves, will convert that into an audible signal, so that we'll be able to hear when we're receiving microwaves there. And I have a little sheet here as well. I won't be using that at the moment. What I'll do first is show you what would happen without a standing wave being formed by the microwaves. So I'm going to turn on the microwaves now, so the microwaves are being sent out. That's us receiving the signal. That's us receiving the signal through the microwave probe. And you can see that's the difference. So I'm receiving a signal, and as I move the probe down parallel to the ray of microwaves, I should see a fairly continuous signal. It may get a little weaker as I move it away, but it should be fairly continuous. So that's what it sounds like as I move it without the aluminium sheet. Now I'm going to put the aluminium sheet here. This will reflect the microwaves back towards the transmitter. So what I have then is two waves of the same type moving in opposite directions, and they have the same frequency and amplitude. So they should meet and superpose in this region, forming a standing wave. The wavelength is about a centimetre, so I should detect, if there's a standing wave, I should detect antinodes and nodes. Nodes will be places of minimum signal and places of maximum signal. So I should get that occurring along here. So I'm going to investigate that now. So I'm getting that oscillating signal that's going between maximum, minimum, maximum, minimum, maximum, minimum. The maximum is where there is an antinode, and the minimum is where there's a node formed. And if I do that more slowly,
This one is attached to a microphone now. So that's why you hear the sound. You can attach to an ammeter to measure the current. So anyway, we have finished that. Any question to ask before we carry on?
You mean move on to A2?
No. We haven't finished AS yet. Hopefully, if we finish AS, you have to stay back another 10 to 20 minutes. We'll stay back.
Okay.
We will do some question. We are at interference, two-source interference. We are in particular looking at Young's double slit interference. Okay. We are looking at the effect of changing parameters. What are the parameters? Y or X, fringe spacing, from center to center of the bright fringe. D, the distance between the double slit is a double slit, is a single slit. There's the screen. So the distance between the screen and the double slit is your capital D. Small d is from the center of the double slit to the center of double slit. Or sometimes textbook will call it A, or your syllabus call it A. Lambda is the wavelength of the light source. So usually this is laser rather than light. It can be shown mathematically. Well, the effect on y, that distance, increasing. We can play with the experiment, moving the screen, increasing d. As d increases, y increases, band widens. As d, the small d, increases, y decreases. As lambda increases, right? We increase this wavelength of the light. Y increases and the band widens. Right? So we can summarize all this with the mathematical formula. We can derive it. But I didn't bother because it's not required in the syllabus. Right? Remember to recognize it. This one, the diffraction is on the horizontal. Horizontal. Vertical, no diffraction. If the slit is horizontal, the diffraction is vertical. Right? Slit is on this side, not on the horizontal length. Laser is a coherent source of light. Each double slit behaves as a narrow slit, causes diffraction. Away from the two slits are the two sources, interfere on the screen. So the interference pattern are vertical. Right? You need to know roughly the magnitude. So this is memory work. Double slit, screen, the small d, slit spacing is about 0.5 millimeter. Very close together. From center to center or from top here to the top to the bottom here. D is the screen slit distance, about 2 meters. Y, your aperture size, which is there, aperture there, is about 0.1. You can see very much larger than the wavelength. You cannot get smaller than that. Fringe spacing. Y is a fringe spacing. Effect of changing parameters. K is a constant. Right? This one is not in the syllabus, but it will help you to understand if you can memorize that. D is the distance. Screen slit distance. Double slit and single slit distance. That distance. Sorry. S is a double slit and single slit distance. That's a double slit. That's a single slit. Remember this is a laser, not light source. Light source it's not coherent source. It's monochromatic also. Right? That's your S. Decreasing S. Make the source of light nearer to the double slit. Bring the source nearer to the double slit, thus increasing the brightness. Right? The source is nearer to the double slit, so you increase the energy. The distance is shorter. The intensity of light is stronger. Brightness of the band increases, but Y is not affected. Y is not affected. It's not in this formula. Okay. Widening the single slit. You widen it. You allow more light to pass through. Increasing the brightness of the band. Increasing the brightness of the bright band. Not affected. Why? Right? It's not in the formula. Right? The widening allow more energy of light to pass through. Further widening will cause the image to be blurred as the source becomes incoherent. Right? Cannot widen too large. Too large, it becomes an incoherent source anymore. No more no more coherent source anymore. Right? If you use point source, point aperture, then you get point source, point interference pattern. If you use slits, then you see the image of the slits. Point source will give the same fringe system, but slits, there is line of point sources, give brighter fringes by reinforcing the pattern, right? Brighter than your uh, round aperture. Increasing lambda, increase y. Right? Remember your wavelength is inversely proportional to frequency. So the fringe spacing for red light is greater than for blue light. Red light has a greater wavelength since y is proportional to lambda. Right? This you must know. Red light greater wavelength than blue light. Brightness of band is constant. That's all you need to know. Even though it's wrong, you're not required to know this one. Band widening. Right? You don't need to know that. It's not wrong, even if you use band widening to argue it out, or intensity is proportional to frequency square. Right? It's not wrong. But yeah, it's not in the syllabus, so no need to know that. Right? This is just extra knowledge. The idea is the intensity for blue light, narrower band, wider band. So the intensity is distributed over a wider band. That's why the intensity becomes for red light is less than for blue light. Okay. The fringe spacing is y is directly proportional to wavelength. Y is proportional to wavelength. Red light has a longer wavelength than violet light, thus have a wider band than violet light. As violet light, smaller wavelength, red light, bigger wavelength. So you have the two light together, violet and red light, it will overlap. So you will see red and violet together at the same time, the red will be at the side there. The same intensity falling on double slit for the red band, the energy is spread over a larger area for red band compared to the violet band. Thus, the energy per unit area is smaller. Thus, the intensity decreases for red band. Right? This is for your info. As I said, you don't need to know about band widening. Slit screen distance, capital D, increasing D, right? Increasing D, you increase Y. And increase D, that's your D, right? That's the distance. R is the distance. D, that's D. So you increase D, you decrease the intensity. Slit spacing, D or A, increasing D decreases Y. Right? That one, increase that, it decrease Y. As Y is directly proportional 1 over D. Brightness remains constant. They haven't affect the distance. Not affect the distance. Intensity is not coming in the equation here. Keeping D constant by increasing the width of the slit allow more energy. If you increase the width of the slit, you allow more energy passing through the band. Thus the band will be brighter. But Y is unchanged. As long as you keep D constant or A constant. Using white light, Right? If you see white light, that's the green light, that's the white light. The center would be white, the center there will be white. Color fringes, colors interfere constructively at the center band. Center band, all the color interfere constructively, but they have different bandwidth. Right? So you see color fringes there. As you look to higher order, then you see higher order fringes will be see different colors, with blue being deviated least, right? Blue deviated least, blue shorter wavelength, deviated least, and red the most, and the others in between. Right? That's why you see all these color fringes there, the edge there, and then all these are because of the different wavelength. Okay, don't think we want to go any further than that. Laser, right? That's what it stands for. Collimated, the beam is narrow. Coherent means you look at any point here, yeah, they have a phase relationship constant. Phase relationship constant. Outside also the same thing. One color, monochromatic, or one wavelength. Danger of laser. This one you need to know for your paper 5 lah. Laser tube operates at high voltage. Do not look, right, into direct or reflected beam. Don't look into the laser beam or the reflected beam. The lens of the eye will concentrate the energy and damage the retina at one spot. The beam should not be directed into a reflective surface like glass. The beam should be directed into a known reflective surface, example, surface painted matte black. Conduct visual laser experiment in a room well lit. Right? Do the experiment in a well lit room. This will protect against accidental damage to the eye. Over there. Explain whether we can obtain interference pattern using two lamps. Can or not? Can or not? Two lamp?
I think so.
No, you can't. Lamp is a incoherent source.
Oh, yeah.
Light source,
But both
example,
lamps are incoherent.
is an incoherent source. Both lamps
Okay.
are incoherent sources of light. Right? Besides, lamp is not monochromatic. Explain whether we can obtain interference pattern with the setup. Right? We use a light source, double slit, and then a screen. Can we do that or not? Can we get interference pattern or not?
I think some can.
You can't. Right? No. A light source or lamp is a incoherent source. Thus, light falling directly on a double slit would not cause interference. Right? It has to be monochromatic. You have to put a single slit in front.
Oh, okay.
Right? A light source, example, a lamp is an incoherent source. Thus, light falling directly on the double slit would not cause interference. A single slit, right? You need a single slit. The purpose of single slit is to diffract the light so that the light falling on the double slit will be from the same wavefront. That's how we make it coherent. Right? From a single slit, the wave coming out will be spherical. So the wave reaching here will be from the same wavefront. And you have to use laser, you cannot use a light source. Right? Laser is monochromatic. Okay, this is for A2 also. Usually if we don't use laser, we use sodium vapor lamp. Right? The average wavelength is yellow light lah. Give yellow light 589.3 nanometer. Right? Basically, it's two lah. This is the average of these two wavelengths. This information you need to know for your paper 5 lah. AS, you just need to know it's a monochromatic source lah. Right? There's your setup. It's a traveling microscope. It can move vertically, can move horizontally. There's your sodium vapor lamp. There's your single slit. There's your double slit. There's your traveling microscope. Okay, we have completed this part. Let us try some question. What is the answer for this one? A monochromatic plane wave of speed c and wavelength lambda is diffracted by a small aperture. There's a small aperture. There's a plane wave. There's a diffraction. Diagram illustrates the successive wavefront. After what time will some portion of the wavefront xy reach P? Yep. What's the time? In terms of lambda and c. Can?
How to do?
AC? That's your wavelength. From wavefront to
Okay.
wavefront length. Right? So from x, y to P is 3 wavelength. Right? Distance
Oh, okay.
then time is distance over speed. Distance is 3 wavelength. Speed is c. The answer is c, right? Can? Anything not clear?
Yeah, can.
This is
Yeah.
came out in 2012, June 12. They do repeat their question now. How about this one? What is meant by diffraction? This is
Fraction.
answer. Yep. What is the answer?
Is it C? Because it's like spreading out.
Right? Addition of two coherent waves to produce a standing wave pattern. That is standing wave, not related to diffraction. Splitting of white light into colors as dispersion using a prism or diffraction grating. The answer is C. C is diffraction.
Oh.
Change of direction when wave across the boundary between one medium and another. That one is refraction. That's your SPM work. The answer is C. Okay. The hue separates the television transmitter, right? TV transmitter from a house. That's a house. Transmitter cannot be seen from the house. However, the house has a good television reception, by which effect at the hue would the TV signal reach the house. This is still 016 June paper 13. Yep.
Diffraction?
Refraction, no? B. Right? This one you need to know what is meant by diffraction of wave, bending of wave, into region of shadow as the wave pass through. And on diagram 2.1 and 2.2 represent the plane wavefront approaching the gap, wide gap and a narrow gap. That one need to remember how to draw. Draw each diagram. Draw on each diagram lines illustrating diffraction to represent the wavefront after passing through the gaps. Okay, that's how we draw. Still plane wave, but spreading out. This one is circular wave. Okay, can
I draw the blue color one, is it?
yeah, you draw the blue color one.
Okay.
Okay, you won't bother about this one. You can do it in your free time. Okay, what's the answer for this one? If you have
In
time,
phase.
will be better.
You want?
What's the answer?
Yeah.
Water wave or wavelength 4 meter are produced by two generators S1, S2. Each generator and operator by itself produce wave which have amplitude of A and P, which is 3 meter from S1 and 5 meter from S2. And the generators are operated in phase. What is the amplitude of the oscillation at P? Calculate the path difference.
Path difference is 2 meters, is it?
Yeah,
Wait, no. Two.
path difference is 2 meter, correct?
Uh-huh.
S2P minus S1P. So, what's the answer? 2 meter is half a wavelength. Yeah, wavelength is 4 meter.
Oh yeah, so it's B.
So, destructive interference. Yeah, wherever you
Yeah.
got lambda, destructive interference. The answer is A. Okay now.
Oh. Oh yeah.
Okay, how about this one? Change it to 7 meter here lah. This one 7 meter.
The path difference is 4.
So what's the answer?
Lambda.
You only got 10 minutes left.
1 lambda.
So full wavelength. So constructive interference. Okay. So A plus A is 2A.
Yes.
Okay now.
Wait. Oh,
Anything
oh,
else?
because there's. Wait,
Constructive interference.
teacher.
A plus A. Yep.
Uh, then the previous question was half lambda plus half lambda. How come is it not just
Lambda is
A,
destructive
C?
interference. You have not reviewed your last week's work. Can or not? If not, I review.
Yeah.
Let's go to the last week's work.
No, I can. Well, I just forgot only other.
Half lambda is destructive interference. Destructive interference, zero intensity, zero amplitude. And
Oh,
constructive
okay.
interference, amplitude is A for each of them, so it's 2A lor. Okay or not?
Okay. Yeah, okay.
You must do your homework, review. If not, you are wasting your money.
Yes.
How about the answer for this one? Can get the answer or not? Use this formula only, that's all. You need to memorize this formula and use it, not to use it. Put in the formula, that's all. And then get the answer.
Okay, yeah, I got it.
Why uncertainty in determining lambda? Right? Because your D a lot of uncertainty, very small to measure. What would the fringe spacing Y be if D is 10 to the power minus 6? 10 to the power 6 nearer to the wavelength of light, lor. Calculate, calculate. What is your Y? Can get the answer. Put in the value, that's all. Same D as before.
Yeah, yes.
Right? It's about Y is very large. You can see that if you use slit spacing,
0.8 meters.
very wide. But we cannot get this small unless we use diffraction grating.
Okay.
Okay, we try one last one. This one. Under which of the following sets of conditions will the separation of the bright fringes of the double slit interference pattern be greatest? Just use the formula only. Just use this formula. Distance between the slits, there's a capital D.
It's inversely proportional. No, directly proportional to
Zero. Zero.
D. The wavelength also.
You want under which following condition, sets of condition will the separation of the bright fringes of double slit, you want the A or the small d be the largest. So you want your what? Right? Just cross multiply. Right? Your D distance between the slits will be large. Sorry. Condition will the separation of the bright fringes of the double slit interference pattern be greatest. You want this one to be largest. Okay or not? Why is
I'm trying to figure out.
why you are looking at Y? You want Y. Sorry, not A or D. Y. Y is proportional to lambda. Wavelength long. Y is proportional to D. That one large. Y is
Inverse to A.
inverse proportional to 1 over A. So A small, that one will be large. Can?
Oh, okay.
Okay,
Yes. So answer is C.
answer is C.
Okay.
It will be cut off anyway lah. But anyway, I will make a start.
Okay.
Right? During your break, you try the question. No? Right? You try this question. 2013, 213, sorry. Okay, our last part, diffraction grating.
Yeah, let me take a
Okay or not? Any problem?
213 question 3142.
Just do the question there.
Okay,
Okay, 37 to 42.
okay.
Right, that's your syllabus. Right? For single slit, narrow slit, your aperture equals to lambda, 180 degrees diffraction. Usually, we cannot get that small near the wavelength. Usually, it's much larger. Usually, the slit is greater than the wavelength. Diffraction is smaller. So Young's double slit, we try to make the double slit narrow slit. Both slits are narrow slit. Usually, the slits are not that narrow. Put it this way. Diffraction grating, thousands of slits per cm. That's how it looks like. That's how it is. You magnify it. Diffraction grating consists of a large number of equally spaced scratches or lines, example 6,000 lines per cm, inscribed mechanically into the surface of the transparent medium, such as glass, where a diamond pointed stylus. Right? So you see the scratches there. Each scratch is an opaque line because the light is reflected through which the sketch grows. Right? Light cannot pass through the scratch line, only pass through the line where it's not scratch. The untouched space between the lines serve as slits. The gaps between the lines are thus very narrow, similar to the light wavelength. Right? After that, you have to explain to me how you get this one in discotheque. How you get all these different color. Anyway, that is your paper 5. Came out 1 year. Right? So you will get marked by drawing the diagram, finding the distance between the wire. Right? Laser is coherent monochromatic light source. In coherent wave, constant phase relationship. Right? That's what you observe, appearance on the screen. As a formula, grating spacing or distance between successive slits, D is 1 over n number of lines per unit length. Right? Try whether you can get the answer for this one. This answer using this formula.